Hi guys, I know we're working on the rotational energy and torque. What my game plan is to get lectures out to you on each of those topics. Hope you got the practice AP test done already, but let's go through moments of inertia and the parallel axis theorem tonight. Well, actually it's during the day for you guys, but this is Sunday night for me. So moments of inertia. So the first one we worked, I'm going to clean it up. We wanted to find the moment of inertia for a uniformly uniformly dense rod of mass m and length L if we rotate it about the midpoint of the rod. So we have a uniformly dense rod. It's going to look something like this. Let me see if I can. It's a little better than that. So we got uniform density of our rod, and the thickness, we're assuming that in the x and y planes we're going to be right through the center. So in other words, we're going to do about a z-plane that goes through this midpoint. This is our midpoint axis, and we're going to rotate this rod about that axis like so. We're going to, since it's a rod, we're going to consider it being basically a line of mass. We're going to treat it for right now like it's a line of mass about the center. And then we can make some arguments about how the moment of inertia in the x and y planes do not actually make a difference on that. So let's start with this. And let's refresh that the moment of inertia is the mass and the radius squared, with some particular coefficient in front of it depending on what you've got. So this is the moment of inertia for a hoop. So if we had a solid hoop, this is R and the mass was m, the moment of inertia for a hoop would be mr squared, because all the mass is located the same distance away, r distance away, and when you integrate across the whole mass you get m. So that's the easy one because it's the mass for a hoop. For the rod, what we're going to do is we're going to come along through here like we said, and we're going to kind of take these little sections. So there's a little section and there's a little section, and this little chunk of mass is going to be the same density as all the other little chunks of mass, and we're going to add them all up together. So my integral is going to be I equals from A to B of r squared dm. So in this case, if we do have this thin rod, this thin circle, like a wire of copper, you know, like in your wiring, it's a really small circle, very small diameter. Let's set up this problem in terms of the work we've got. So we're going to apply an axis here. So here's our axis, and right through the center of each one of these is going to be our axis. And of course you have another axis that runs through like so. And so what we've got in this problem is we want to figure out what a chunk of mass is represented by here. So each one of these little chunks of mass, we're going to treat them as individual masses, and we're doing uniform density, so that lambda is total mass over total length. Okay, since it's a rod, it would just it would be just as easy to do sigma, which is the area density statement, and we could do total mass over the area of a circle, which is pi r squared. It's another way to work the problem. But we're really treating this like it's just individual bits of mass along a line. So here we go. What does our coordinate system do? Well, if I make this 0, here's my origin, then this end over here, this location would be negative L over 2. This location over here would be L over 2. And so we'll integrate from negative L over 2 to L over 2. And now we've got to figure out what our radius is. The radius is always going to be how far your chunk of mass is from your origin. So in this case, my radius would go from the origin to the chunk of mass I pick. And so, by the way I've set up my coordinate plane, that's just an x value. So x squared. And then last but not least, we've got to figure out what a chunk of mass means in this scenario. Well, if we really have a line, if we really have a linear density, then lambda times L equals m. We take the derivatives of both sides, so a chunk of mass is directly proportional to a chunk of length. But in our case, that's going to be a dx. So based on our picture, we go over some amount x, so we go over here to some x value, and we cut out a little sliver of this x. This little tiny sliver with a thickness of x is going to be our linear density piece. And we're going to do this with disks to get cylinders in a little bit. So here's our x squared. dx, or dm in this case, is lambda dx. And so now all we have to do is integrate, which actually tends to be the easiest thing that we do on these problems. The setup tends to be the worst part. So the integral will be lambda, which is a coefficient, x cubed over 3, integrated from negative L over 2 to L over 2. So I equals, now we're going to unsubstitute so we get back to our original variables. Lambda is m over L. X cubed over 3, when we do the first part, it's going to be L cubed over 8 over 3 minus L cubed over 8, this one's negative, over 3. And you can see that what we get is m over L times, these two turn into a positive, 2L cubed over 24. And when we reduce the fraction, we get m L squared, one of these cancels, and 2 and 12, leave a 12 on the bottom, get 1/12 ml squared. So there's our nice clean version of what we were talking about during our RTI. So to add to that, all of our answers, when we do moments of inertia, all of the answers will have this form. They will all be a mass times a radius squared. Now occasionally on the AP test they make up some weird function of density, linear density. They don't give you a uniform density, they give you some funky equation that goes with the density. And we'll try to work one of those before you take your semester test just so you can see them. But all the rest of them are going to have this form. Now, let's say that instead of that, we now want to rotate this object, this line of charge that we have. Now I want it to rotate about this axis, which is further away. So what are we going to do here? If I want to spin it around that axis, let's get that a little bit cleaner. I want to spin it about this axis. Now, it's like my rod got longer, because if this is my axis, my radius now goes from 0 to L. And now I've got to add all these little pieces. But what I'd really like to do is just know one of these and be able to shift the axis any which way we want to go. So there's this cool thing in physics, because this has been around for a while, right? Physics problems have been around forever. we wanted to figure out how to do this problem without actually having to do the calculus every time we get a rod. We want to have a rule that works for, hey, I put my axis here or there, I put my axis there, no big deal. So what we have is what we call the parallel axis theory. And it does exactly what you think it should, which is, if I do the moment of inertia here at this axis, and then I just move the axis over here, can't I just change the way we counted x somehow and just add something? Because all we really are doing is making the radius, instead of going from 0 to L over 2, or from negative L over 2 to go up to L over 2, we're making our radius actually go all the way up to L. So we've just increased our range, if you will. And so here's what the parallel axis theorem says. The new axis moment of inertia is the original axis moment of inertia plus shift everybody to the new radius. Okay? And what we're doing here is we're having a constant value to weight the new distance. So, here we go. We started with, remember, this was 0 to L over 2, and on this side to L over 2. And now we're going to go from 0 to L. So we took our axis that was here, and we've put up and moved it L over 2 to the left. Okay. Alright, so here we go. What's my new one? It's my old one. 1/12 ml squared. And here's going to be the add. We're going to add the new amount of distance. So here's what we got. What's the mass? We're going to shift all the masses. How far are we going to shift them? We're going to shift all the masses L over 2. So I'm going to add that extra, hey, we've added a change in position thing. Just like you do horizontal shifts or vertical shifts, you know, on a number line or a coordinate plane. We're just going to shift our axis, and we're going to put in, the mass is now acting this much bigger. So what do we get now? Well, we get 1/12 ml squared plus 1/4 ml squared. So let's see, this would be, we do a little algebra here. 3/12, this becomes 4/12 ml squared, which is really just, can you do it? 1/3 ml squared. And now you have the new axis. If you look this up in the book, that will be the answer you get for the axis being over there. And what's super cool about the parallel axis theorem, of course, is, let's say that I wanted to make my new axis 1/3 L. Okay, no biggie. New is old plus shift all the mass how far? Well, if I'm at 1/2 L, how far is it if I'm moving it to 1/3 L? Well, let's see, this is 3/6, this is 2/6. So I've really shifted it 1/6 in distance. So 1/12 ml squared plus 1/36 ml squared. And now I have, this is 3/36, so I have 4/36 ml squared, which equals 1/9 ml squared. This is pretty awesome. So it's a pretty awesome little theory, because that allows us to take any number of axes and move them wherever we need them to go. In fact, it's even as easy, and we're going to do the disk here in just a second, but let's say we have a disk, right? It kind of comes over there, and there's the back of our disk. So here's our thin disk. What if I have my axis in the center, which is what we're going to do the calculus for in just a second, But what if I want to move it someplace over here that's like 3 and 4? I've moved it 3 this way and 4 this way, and I want my axis over there now. Well, how far is 3, 4 from where you started? Well, it's 5. So then you're just adding, whoops. You're just adding, now shift all the masses 5 units from where they were a minute ago. So it doesn't, you don't have to do anything fancy to fix it. You can just actually move it. Now, what would be super cool is if we could rotate this axis, and the parallel axiom theorem would be like a rotational one too, but we don't. You may notice it is called the parallel axis theorem. So this only works if your new axis of rotation is parallel to your old axis of rotation, meaning that you can't use it if you have, here was your original axis of rotation, and now this is going to be your axis of rotation. You cannot do it when you shift it like that. That will not work, okay? So you can only do it with parallel axes, but it's a very powerful tool to save you time and energy when doing calculus. Okay, so let's look at one more. And then you guys will have time to play with this, but we will work some problems. We'll just work some AP problems with torque and rotational motion to get you a feel for them. We're mostly going to be spending, I've got to do, we need to do physical pendulums, and we might need to look at pendulums and springs a little bit more, but we'll try to do that on the next lecture. So we'll do some a couple of practice problems and things like that. So let's say we have a disc. Uniform disc. With radius, big R, mass, big M. And it's going to be, we're going to do the easy one, rotated about the axis through, sorry about that, the center of the circle. Okay, so here's our picture. Let's actually do this. This will help me do this a little bit cleaner. Okay, I want to make that no fill. Come on, man. No fill. I do want the outline to be a little bit heavier weight. Go. Okay, so now we've got here's our disc, and we're going to rotate it about the center point. Okay, so it's going to go all the way through the center point. So if we look at this as a face-on drawing, we look top down, where we're rotating is we're rotating about a point directly in the center. So we're just drawing an axis that goes like that, and our disc, kind of thickness on this side. On the back side there'd be some thickness. So the question becomes, how are we going to do this, and what's the easiest way to do this? Well, I think personally, and when you're doing this kind of problem, you take advantage of symmetry as much as you can. And so the symmetry that we're going to want to deal with here is going to be the radial symmetry, meaning that what I want to do is cut out, if you will, whoa, that was terrible, that I want to start cutting out little rings of matter And since all those are at the same radius, then add all that ring's mass together to all the mass for the ring for the next one, to all the mass for the next one, and so forth and so on, so that it's a lot easier for us to actually integrate. Because it's clear that you can't, I don't want to just come along and go, hey, let's pick this point here and this point here and this mass here and add those together. That's going to be a nightmare to try to write a calculus integral for. So, once again, we're going to start with moment of inertia is the integral, and what we've got to decide is where's our 0 going to be? Well, clearly we want to put x equals 0 here, and x equals r there, so this is going to be from 0 to r, and it's r squared dm. But we now have to take an idea of what this mass chunk is. Okay, so if I take a piece out of here, and I take that particular little ring, right? Let's get this disc a thickness of h, just for argument's sake. That little ring, when I cut it out, is actually a cylinder. So as I'm doing this as a circle, I'd use if I was doing this as a flat sheet of circle, it'd be one thing, but we want to do a disc. So a disc is going to have a little bit of thickness here. So where is our cutout going to be? Well, when we look down from here, the thickness of each one of these lines is going to be our d what? That's what we've got to figure out. How thick is that? Well, that's our, I'm going to call it dt for thickness. So what is the size, how much mass is captured in this cylinder? Well, the volume of a cylinder is, if you recall, pi r squared h. That's the volume of a cylinder. So what we have is it's going to be the volume of our disk is going to be a pi r squared h. But what's the piece that's going to be changing for us? What's changing for us? The radius. So we're going to have an inner and outer radius on this thing. Okay? So is there a way maybe to get that so it's not quite such a problem? To figure out the volume. Well, let's see. We said it's a uniform disk, right? So what if I do this like so? Area, let's go back to our setup for a second. Let me move some of this stuff out of the way. Let's leave this thought over here. This is sort of in our pile of thoughts. What if we do a thin disk and we slice it so that dt goes this way? In other words, we actually do a sheet. Do I have to then still do I have the same problem I had a minute ago? Well, you're going to have to choose how you want to do this. You can slice a disk perpendicular to the disk. In other words, you could slice it like this, which would give you cross sections that are circles. Or you can make little cylinders and build the cylinders from inside to outside. The easier way to work with a disk is to use this idea of, if you like, slicing the volume up into circles. So that's really kind of what we're going to do. Okay? So how are we going to do that? Well, sigma, area density is total mass over total area, which would be capital R squared. So pi times, or sigma times pi r squared is m. So dm would be sigma times pi times 2rdr. There's your derivative. Okay. Now what does that chunk of mass now represent? That chunk of mass now represents the top sheet of the cylinder. So instead of trying to cut it through the middle and do radiuses inside radius, outside radius, and all that, it's going to be a little bit easier if we slice it, in this case horizontally because of the way I've drawn the picture, and make a lot of thin little discs. Tiny thin little discs, with each disc having some amount of area. Okay, I can live with that. So here is our area setup. So what are we actually going to be integrating if we do it this way? Well, we still want to find the moment of inertia, yeah? Is that going to help me find moment of inertia if I do it with area? Well, it makes integrating to find volume way easier. But each one of these sheets has various distances from the axis. And so even though this feels like a really good way to go, to slice it horizontally and make all these nice sheets, each sheet is not the same distance away from the axis. So although this seems like the way we're going to go, we're going to have to do it the way we stated, which means we're going to have an inside axis, inside radius and an outside. So I'm going to erase this picture real quick. No. Well, let's just redraw it. It's easier. Shapes. So give me a second to get this drawn. I'm going to draw another circle. Over here. Let me get it a little bit closer to what I need. Okay, so now what we're going to be integrating, as I showed in this picture, is this little thing. So we're going to figure out where the mass is, and for each one of these little pieces, this cylinder, all the mass along that cylinder will be the same radius away from the axis. So that's what we're going to work with here. So let's go down to this picture. So on our picture, this is the outer radius, and this is the inner radius. And so this thickness that we're talking about is actually a dr. So we're going to capture that piece with dr. How are we going to capture the rest of it? Well, here what's changing? Radius. So V equals pi r squared h. So when we do this with volume density, here's how this is going to look. So volume density is the Greek letter rho. Looks like a P, and it's going to be total mass over total volume, m little h, and the r is squared. So pi rho r squared h equals m. So dm is pi rho pi 2rdr, because now this is the one that's moving. So this is a chunk, remember, 2rdr times h. That's going to be a chunk of mass, and dr is our variable. So what are we going to integrate from? Well, as we said, we're going to go from 0 to cap r. dm is going to be 2 rho pi r dr h. And what is our distance? Well, here's the cool part. The distance from the axis now is just r, little r. Let's make these little r's to reduce the already confusing mess that we have on our plate. So here is our integral. So let's pull all this out. What can come out? 2 rho pi h. What stays in? r squared, and dr. Woo! It's a big mess on our hand. A lot of constants going on. The integral of r squared dr, as you know, is r cubed over 3, evaluated from 0 to cap r. Okay. So you may be wondering, how do we unpack all these pieces? Well, 2 rho pi h, this will be cap r cubed over 3 minus 0 cubed over 3. So we get 2. Density, rho, as we've been using it, is m over pi r squared h, and it's capital R squared here. Then there's pi h over 1. There's a 2 over 1. There's a pi. And h are over 1. And all of that gets multiplied by r cubed over 3. I feel like I'm missing a 2. The answer should come out 1/2 m r squared. I feel like I've lost it somewhere. Okay, so we got pi is going to cancel, h is going to cancel. This one should have been a 6. Not sure where I've lost it. We'll go back and look at it here in just a second. So 2 r's cancel. Yep, that's what it is. That should be r to the 4th over 4. Hang on, let's go back up here. Volume of a cylinder is area of the base times the height. Area of the base is pi r squared. Height. Oh yeah, we need to do the inner and outer r's. Okay. Hang with me for a second. I'm going to pause and check. Hey, sorry I had to stop talking so that I could see what my mistake was. If you'll recall, the moment of inertia equation, a to b is r squared dm. So this r is squared to start with. I just got careless in copying my definition. We've been doing the centers of mass for so long, I forgot to put that in there. I put it right here. I had it up here, but then I just didn't copy the r. So now we're good. So this does actually come out like we said. It comes out to be r cubed dr, because you get 2 here and 1 more from your density, which then gives us same stuff. Whoops. Same stuff, but 4th power. So let me redo that. Y'all probably caught that while I was doing it, and since you're not here with me, I didn't see that I just miscopied. Ah, the joys of being back with you in person. It's going to be so good to have you guys, to have me back in the room and have y'all in the room with me. 2 pi density h. This is now r to the 4th over 4, which we get r to the 4th over 4 minus 0. So we get, nicely, 2 over 1 times mass times pi r, capital R squared, h, times pi over 1 times h over 1 times r to the 4th over 4. Now we can simplify. pi cancels pi. 2 of the r squareds cancel out and leave me r squared over here. 2 cancels out with the 4 and leaves me a 2. So my moment of inertia of a disk is 1/2 m, oh, and the h's cancel, r squared. So even though we really would have liked to use sheets of paper idea here, we couldn't. Now, I'm going to give you a tip-off on what you do with a sphere. I'm not going to do the sphere on this video because it's already long enough, but it gives you an idea. I'll work problems next time. If you do a sphere, what you actually do is you do disks. You set all of these as little disks, setting one on top of each other where the disks are getting smaller. And you integrate top to bottom, so from positive r to negative r, where this is, like, this might be your axis of symmetry that you're going to rotate about, and then you go out to each one of these little discs and make a triangle. It's really pretty hideous trying to draw the picture for this. And of course the nice thing that happens is the end result is 2/5 mr squared. But you have to go through a ton of algebra on this one to get there. It's not that the calculus is the hard on the sphere, it's that the algebra gets to be pretty testy and it's really easy to mess up your fractions. So maybe I'll do that on another one, or you can look that one up for yourselves. But the 3 I would memorize for the test is I would memorize the rod about its center, the disk, and the sphere. Because if you have those with the parallel axis theorem, you can literally find every other moment of inertia regardless of where you put the axis in 3 space. Alright, so that's all for now, and I'll catch you guys hopefully in RTI the next couple of days or tonight. Talk to you later.